Good. Sorry. Okay, I don't know why the tables in a row sort of migrate around. Okay, so today is very exciting. So today what we're going to do is begin our discussion of the Standard Model. And in particular, what I'd like to focus on is what's known as the electroweak theory, which, well, that's the part of the Standard Model that you haven't seen yet, because we've already spent some time studying Yang-Mills theory, and the strong nuclear force is described by an SU3 Yang-Mills theory. Nothing particularly fancy about it, except for the fact that it's asymptotically free, and hence infrared strong, so it has all sorts of complicated effects at low energy that we don't understand. But still, it's a rather simple, at least in principle, gauge theory to study at high energies. Today, however, I want to continue with our discussion of last time when we introduced the Higgs mechanism to describe, I think, probably the most famous and interesting application of the Higgs mechanism. That is to the description of the electroweak force in the Standard Model, originally developed by Glashow, Weinberg, and Salam. Okay. So the Standard Model of particle physics also often goes under the name of the Glashow, Weinberg, Salam model. So there's a sense in which you now have all of the ingredients in front of you, so that there's a sense in which I could give a lecture on the Standard Model of the particle physics in 5 minutes and then just end. Okay. Because it's possible, given what you know, to very succinctly summarize the matter content and interactions of the Standard Model. And to some extent, all I'm going to be doing this week is writing down the action of the Standard Model, parsing it out in some detail, giving some special names to the objects that appear here, to the various fields that appear here, so that you can then make contact with some of the things that you may have already heard about the Standard Model of particle physics. So in any case, as you surely know, the Standard Model of particle physics has forces, which are described by gauge fields. The gauge group is SU3 times SU2 times U1. SU3 here describing the strong force, and the SU2 and U1s describing the electroweak force. The important thing to keep in mind about the Standard Model is that this U1 symmetry is not electromagnetism. The U1 gauge theory, when we write out the SU3 times SU2 times U1, is not electromagnetism, but rather is something that we refer to as the hypercharge gauge symmetry of the Standard Model. And what we think of as electromagnetism is some linear combination of hypercharge along with some U1 that's sitting inside the SU2 group. Okay. This is something that we'll see in a little bit. This is a consequence of the Higgs mechanism. So that's the force carriers of the Standard Model. We also have matter fields, which are spinors. They're all spin 1/2. And they are left-handed Weyl spinors that transform in some representations of the gauge group. And so, in particular, there are 3 copies, often referred to as generations, of a particular matter sector. So I'll just write out what the representations are. So here, first I'll write out the leptons. So here I'm writing them as a collection of 3 numbers. So the first index is the SU3 representation. The second is the SU2 representation. The third is the U1 representation, that is to say the value of hypercharge for this particle. So these are the 2 leptons here. They're leptons because they are SU3 singlets. So leptons, by definition, are particles that don't carry color charge, that don't carry an SU3 index. And in this first case, we have a doublet, which is the lepton doublet containing the electron and the neutrino. And here we have the positron. And we also have some quarks, which have now some electroweak charge as well as color. So here we have the right-handed quarks up and down. Here we have the left-handed quark, the anti-quark U bar and the anti-down D bar. So these are the matter fields of the standard model. And then there's one more field in the standard model, which is a complex scalar field. And this complex scalar carries charge. It's uncharged under SU3, but it carries both color and it carries both electroweak and hypercharge charge. So it's really a doublet of complex scalars, referred to as the Higgs field. So these are the fields of the standard model. You've got a bunch of gauge bosons, a bunch of spin 1/2 particles, and a complex scalar. And what are the couplings? Well, the couplings, what are the other terms that arise in the standard model? Well, they're exactly what you would expect from our discussion of renormalization. So we include in the couplings all terms of dimension less than or equal to 4. That is to say, all of the relevant terms in the action which will survive at low energies, allowed by the symmetries of the theory. So by Lorentz invariance and gauge symmetry. So that's it. That's the standard model of particle physics. Now, of course, there are many undetermined couplings in this model. So all of the various gauge couplings for those 3 gauge groups, as well as all of the various couplings for the interaction terms. And most of these couplings have been measured to various degrees of accuracy, most but not all. And to some extent, that's it. There's nothing, it can fit on a single slide. Okay. You could write it on the back of a t-shirt. In fact, I'm sure that you can buy a t-shirt with this written on the back of it. So to some extent, what I want to do today, and perhaps a little next class, is just write out this model in a bit more detail. Okay, so that you can kind of get a feeling for what all the various particles are, how they interact. Along the way, we'll meet lots of, to some extent, this is a lecture where I'm just introducing a lot of terminology, a lot of special names for certain fields, things like electrons and neutrinos and muons and leptons and stuff like that. But I'm not, this class, going to explain too much of, for example, where these various numbers come from. Okay? So for example, why is it that we happen to have, fields transforming in these representations as opposed to other representations? Okay? Now, there are some hints that we have that allow us to determine some of these numbers. Why do we have SU3 times SU2 times U1 as opposed to some other gauge group? Why do we have this particular configuration of charged particles as opposed to some different configuration? There are some things that are well understood. So for example, if you want all of your gauge symmetries to be non-anomalous, okay, not broken by quantum mechanical effects, that actually is a very strong constraint on your matter content. Okay. Moreover, it turns out that you can also think about discrete symmetries of the standard model that help you understand some of these hypercharge assignments. And finally, I think my favorite way of thinking about the symmetry structure of the standard model is thinking in terms of grand unification. Okay. So for example, if we have a chance next class, what I'd like to do is talk a little bit about how you can assemble all of these various complicated random-looking representations of the standard model gauge group into a very simple representation of SU5 or SO10. So that, I think, is probably the cleanest way of thinking about the possible origin of the matter content of the standard model. But for now, what I'd like to do is sort of take a somewhat more practical point of view and just take this as given and just work out some of the consequences of this. So in particular, what I'd like to do today is start with the electroweak sector. So let's start with SU2 times U1. And in fact, as you hopefully remember, SU2 times U1 is the same as U2. Okay. So you can think of the electroweak gauge field as a 2x2 complex matrix with elements in the group of 2x2 unitary matrices. And the important point is that we have a scalar field phi which transforms in the two-dimensional representation of SU2. And it acquires a vacuum expectation value which breaks the gauge symmetry down to U1. And it's this U1 that we know and love. This is the massless remnant of the symmetry breaking, which describes electromagnetism. So now why does the Higgs field acquire a vacuum expectation value? Well, we're instructed here to include all of the terms in the action for the standard model that are allowed by Lorentz invariance and gauge symmetry, which means that the Higgs field phi should have a potential. So what will that potential look like? Well, it's a complex scalar field, so it'll involve things like phi dagger phi, and it will have a quadratic term and a quartic term, which, if we just add an overall constant to the standard to the Lagrangian, which we don't care about, can always be written as a perfect square, as I've done here. Okay. So that will have a minimum. Where phi has some non-trivial vacuum expectation value that I will call V. Okay. Now here I'm using a global U2 rotation in order to set this vacuum expectation value to be purely in the upper component of this two-component doublet. So I can always do a change of, so, you know, if your vacuum expectation value does not is not purely in the upper component, you could always do a field redefinition to put it in the upper component. So there's no loss of generality here. The only thing that I am assuming is that the parameters in V are such that phi has a minimum, which is that this V of phi has a minimum which is non-zero. Okay. Why does V of phi have a minimum that's non-zero as opposed to one where phi is equal to 0? You know, that's a mystery. Okay. We're instructed just by the general principles of renormalization to write down an arbitrary effective action. So expanded around phi is equal to 0, you expect a term, an m squared phi squared term. Okay. Why is that coefficient m squared negative rather than positive? Well, you flip a coin. Half the time it's going to be positive, half the time it's going to be negative. It turns out that in our universe it's negative, so that we have a broken SU2 times U1 symmetry. To some extent, you know, the standard model of particle physics is filled with little mysteries like this. You know, there are a lot of there are you know, almost 20 undetermined. Sorry, there are almost 20 coupling constants in the standard model of particle physics, and you know, there's no real principle that allows us to determine these coupling constants. And there's sort of a whole industry of people who look at these coupling constants and squint a little bit and say, well, this coupling constant's pretty small. Let's try and see if we can come up with an explanation for the smallness of this constant in terms of a symmetry. Stuff like that. And in many cases, these are convincing, and in many cases, they're not. But from a practical point of view, you can just take the Lagrangian of the standard model as given. And that's what we're going to do in this class today. Okay. So we have a potential for the Higgs boson, which has a non-zero vacuum expectation value. And so that means that the SU2 times U1 gauge symmetry will be broken. And in particular, the kinetic term. So what is the kinetic term? You know, it's d mu phi dagger times d mu phi will lead to mass terms for the gauge bosons when we expanded around the non-trivial vacuum expectation value for phi. So in particular, it's sort of convenient to write this all out in matrix notation. So, you know, when talking about quark field, when talking about gluons, you know, it's sort of troublesome to write down 3x3 matrices, but 2x2 matrices are not so bad. So let's just go ahead and write it out. So what does the kinetic term look like? Well, here, let me just use components for a second, or no. Maybe I won't use components. Maybe I'll write it out using fields. Okay. So d mu phi, what is that? Well, that's the ordinary partial derivative of phi plus a gauge coupling term. So phi, as the Higgs field phi, is charged under both SU2 and U1, so it couples both to the SU2 gauge field via some representation matrices 2A, as well as to the U1 gauge field. So here the TAs are the SU2 representation matrices for the two-dimensional representation, okay, otherwise known as the Pauli matrices, right? Pauli matrices are the representation matrices for the two-dimensional representation of SU2. And here, A mu A, these are the SU2 gauge fields, and B mu is the hypercharge gauge field. And Y is the value of hypercharge for the Higgs field, which is just minus 1/2. Okay. So Y is just minus 1/2. And G1 and G2 are the gauge couplings for the SU2 and U1 gauge fields, respectively. So let's write that out in a little bit more detail. Okay. So what is this? If you want to write it, think of it as 2x2 matrices. You have d mu phi plus, let's call it minus I over 2. So I'm just going to write this all out a little bit explicitly. So we have G2 times A3 mu minus G1 B mu and minus G2 A3 mu minus G1 B mu in the two diagonal components, just using the expression for the Pauli matrix of sigma 3 is proportional to 1 and minus 1 on the diagonal. And on the off diagonals, we have G2 times A1 minus IA2. And here we have its complex conjugate, A1 plus IA2. So just to keep myself from writing this matrix down again, let's just call this matrix M. And then in order to figure out the mass term, we need to just expand the kinetic term. So d mu phi dagger times d mu phi. So the leading term, the one that gives the mass term for the gauge bosons, is just found by plugging in the vacuum expectation value for phi into this kinetic term. So what do you get? Well, you get, so the vacuum expectation value for phi was right up here, so it was 1 over root 2 times v0. So what do you get? You get minus 1/8 times v squared times 10 m 10 plus dot dot dot. And this is here then the thing that gives you the masses for the gauge bosons. This is just the Higgs mechanism. And what we need to do now is diagonalize this mass matrix. Any questions so far? So right now I'm just working out an example of the Higgs mechanism as we had introduced it last class. Yes, question?
So if we have a group that is a cross product of two groups, then the covariant derivative just take the form that the connection term is just a...
Absolutely. If your gauge group, yes. So if you think about it, hopefully that's more or less clear. If your gauge group is the tensor product of two groups, then you have a representation theory index. So your matter fields will transform in a representation of each group, and you get two indices, one for each group. You get so let's call your gauge groups G1 and G2. You get, say, an I index for your representation under G1, a J index for your representation under G2, and the total connection is just the sum of the two. Okay. And that's all that I'm doing here, but I'm using the fact that I can actually, SU2 times U1 I can sort of think of as U2. And so in this case, I mean, this is a statement that you're familiar with. In this case, I'm really thinking of this Y here not as just minus 1/2, but as the 2 by 2 matrix, which is minus 1/2 times the identity matrix, the 2 by 2 identity matrix, if you want to think about it that way.
So are there any cases that the connections are mixed or there are cross terms?
If there are cross terms, then that really means you don't have two gauge groups, but one giant big gauge group, if you know what I mean. Now, if you wanted to add gravity into the game, okay, what would you do? Well, for those of you who've taken general relativity, it's sort of obvious. What you would do is you would add to this not just a gauge connection, but a covariant, a Christoffel connection, okay? The covariant derivative terms of general relativity. That's just another kind of connection. Now these the Higgs is a scalar field, so the Christoffel connection is just the usual partial derivative in that case. But if you were writing down the kinetic term for the gauge fields, those are vector fields, and so you would have a Christoffel connection there. So yeah, good, excellent question. Any other questions?
There is
Yeah.
a
M, yes? Yes, what's the question?
another M dagger.
Oh, M dagger M. Yes, I'm sorry. Okay, good. Thank you. So M dagger M. Sorry about that. Good. Okay. So we can now diagonalize this. And to some extent, diagonalizing the mass matrix is a straightforward exercise in manipulating 2 by 2 matrices. So I'm not going to go through all of the details. The idea is that if you just work out what M dagger M is, and you multiply it by these vectors V dagger V on the left, or you multiply it by the Higgs vacuum expectation value on the left and the right, well, what will you get? Well, what you'll find is that there are 3 massive gauge fields and 1 massless gauge field. The massive gauge fields, well, it's sort of easy to see what two of the massive gauge fields are. So in particular, if you just look at these off-diagonal terms here, and you multiply m dagger m, what you're going to get is a product of a bunch of A1s and A2s. So A1 and A2 are going to be massive. And it's sort of conventional to think about not A1 and A2, but to organize them into a pair of complex fields rather than two real fields that are called the W bosons. And as we'll see, it's convenient to talk about them as complex vector fields, as one complex vector field rather than two real vector fields, because they're going to carry electromagnetic charge, as we'll see in just a minute. We have four vector fields. So there's also going to be one of them is going to be massless. I'll call that one A mu. That's going to be the photon of electromagnetism. And so the W's span A1 and A2. So we now need to, so the vector field A is going to be some linear combination of A3 and B mu. And so I'll just write it as sine theta W times A3 plus cosine theta W times B mu, where theta W is some angle called the weak mixing angle. And I have a sine and a cosine there because I want my field to be canonically normalized. Okay? So I need to have a sine and a cosine there because sine squared plus cosine squared is equal to 1. And then there'll be one other mode, which is sort of transverse to the electromagnetic linear combination, whose coefficients are cosine and minus sine. And then you can then go through this straightforward procedure of diagonalizing the mass matrix. And what you'll find is that the matrix is diagonal for a particular value of those coefficients sine theta and cosine theta. So in particular, when this weak mixing angle is the inverse tangent of G2 over G1, the mass matrix is diagonal. And in particular, so just writing it out a little bit more explicitly, we can pull out a factor of G2, because remember, almost all of the coefficients in this matrix M were proportional to G2. We only get some factors of G1 over G2 appearing, which is otherwise known as the sine of the weak mixing, or 1 over the cosine of the weak mixing angle. And so we get, well, what is that? That's 1, 0 times something involving Z mu up here, and W plus and W minus down here, and something else down in that lower corner that we don't care about because it gets multiplied by 0 anyway. Sorry, I guess I have to square that matrix. Okay. So that matrix, okay. Sorry, I don't have quite room to, okay, screw it. We'll just write out, so that times its dagger over here. And so if you write it all out, you get a mass term for the W bosons plus a mass term for the Z bosons. And I've introduced a relative factor of 1/2 here, because really I'm thinking of these W's as being a complex vector field. And just like, if we were to write a complex boson, you usually don't put that factor of 1/2 in front of the mass term. That 1/2, usually the combinatorial coefficient that you normalize you put in front of a coupling term is 1 over the number of symmetries of that term. So for a phi squared term, you can interchange phi, so we put a 1/2 there. For phi bar phi, you can't interchange the two, and so you don't put a 1/2 there. So that's just a convention. So here, the W mass is V over 2 times G2, and the Z mass is the W mass divided by the cosine of the weak mixing angle. And observationally, these are both a little less than 100 GeV, so the W bosons being slightly lighter than the Z bosons. And so comparing those two, the weak mixing angle is pretty small, but not that small. So maybe I can just summarize here. So what we started out with was a Higgs field phi with 4 degrees of freedom. And we had 4 gauge fields. But after these gauge fields get Higgsed, because phi acquires a non-zero vacuum expectation value, 3 of those real scalar, so 3 of those gauge fields become vectors, become massive vectors, and so they eat 3 of those would-be Goldstone bosons from the broken symmetry of phi, and so we're left with 1 real degree of freedom in phi, which is known as the Higgs field. So, there's a slight perversity of notation here. Sometimes we, by Higgs field, refer to the full complex doublet. But really, 3 of the components of that complex doublet are the same as the longitudinal polarizations of the W and Z bosons. And so, typically, when we say Higgs field, what we really mean is the 1 degree of freedom left over. And when we say we observed the Higgs boson, what do we mean? We mean that we observed the particle that's created by fluctuations around the vacuum expectation value of this real degree of freedom left over after the Higgs mechanism. So in particular, the way that we usually write the standard model is in unitary gauge. So remember what unitary gauge is. Unitary gauge is the one where we absorb all of the fluctuations around the vacuum expectation value for phi that we can into the gauge field. Okay, so we interpret those 3 of the 4 degrees of freedom in phi as the longitudinal polarizations of the massive gauge bosons. And so you're only left with 1 degree of freedom in phi, which is the degree of freedom that can't be absorbed by a charge rotation, by a U2 rotation. And if you think about it, the only degree of freedom in the complex doublet phi that can't be absorbed into some U2 rotation would be a change in the magnitude of phi. So that means that we have 1 real field left over that I'll call H, which is just the measuring the size of the vacuum expectation value of phi. So H is a real scalar known as the Higgs field. And in unitary gauge, you can write out what phi is. So it's 1/4 lambda v squared h squared. That's the quadratic term for the Higgs field. Plus there's a cubic term and a quartic term, where the quadratic term sets the mass of the excitation around this vacuum. And famously, this mass was only recently observed. It's about 125 GeV. There are sort of strong theoretical reasons to think that the Higgs boson mass had to be about the same order of magnitude as the W and Z boson masses. In fact, there are many theories which predict that the Higgs boson has to be less massive than the W and Z bosons. So the fact that the Higgs boson is somewhat more massive than the W and Z's already caused some tension with a lot of extensions to the Standard Model, but it is what it is. There, in fact, I mean, it's sort of interesting. Before the LHC, back when you were all children, the cutting edge accelerator was the Tevatron at Fermilab, and everybody, was sort of surprised that they never saw the Higgs at Fermilab, because before the Tevatron, the bias was that the Higgs was actually going to be lighter than the W's and Z's, but that didn't really turn out to be the case. Okay. Any questions before I continue? Everything more or less straightforward? Good. Okay. So the next thing that I want to do is what I would like to do is understand what the coupling constants, what the dynamics of these W and Z bosons look like from the low energy point of view, okay, from the point of view of electromagnetism. So in particular, the action describing the gauge fields is just the normal action, okay, of a Yang-Mills theory. So minus 1/4 f squared, where f here is now the curvature of the SU2 gauge fields, and b here is, well, d mu v nu minus b nu d nu b mu. And it's a reasonably straightforward exercise to go ahead and write this all out in terms of the W's and Z's and the electromagnetic gauge field that we wrote down above. Okay. So in particular, we had those mass terms. We diagonalized the mass matrix. That was some change of basis for these fields. And so now you could just go ahead and write all that out in terms of the W's and Z's. So in particular, just to give you, I'm not going to go through the entire computation, but I'll just give you a little bit of a flavor for it. Okay. So in particular, we had that, so let's see here, Z and A were some linear combinations of A3 and B. So that means that you'll get a term here, you'll get a standard minus 1/4 f mu nu squared, where f mu nu is d mu a nu minus d mu a mu, so that's the standard kinetic term for electromagnetism. And you'll get a minus 1/4 z mu nu, where z mu nu is d mu z nu minus d nu z mu. And then you'll get some terms involving the W bosons. So you'll get a d mu W nu minus times d nu, well, d mu W nu plus various complex conjugates. And in order to work out exactly what this term is, what we would need to do is you would need to, well, start by expanding, say, this term right here, okay, using the fact that f mu nu 1, what is that? That's d mu a nu 1 minus d nu a mu 1 plus g2 times a nu 2 a, sorry, let's call it a mu 2 a nu 3 minus a nu a mu 3. And then you would need to go ahead and plug in our expression for a mu 3 in terms of a mu, the electromagnetic gauge field, and z. And then you would get some coupling term between the W bosons and some linear combination of z and a. And what linear combination would that be? Well, I'll just write down the answer for you so that we don't have to bother going through the answer. So here, d mu W plus, say, would be d mu minus I g2 a mu 3 times W plus. So this will be d mu minus I g2 sine of the weak mixing angle times A plus cosine of the weak mixing angle times Z. Okay. So this, of course, linear combination being A3. Or if you want to write that out a little bit more succinctly, the gauge covariant derivative is d mu minus IE times a mu plus the cotangent of the weak mixing angle times Z, all acting on W. So the important term that we want to pay attention to is this term right here. What is that? That term tells us that the W plus boson has an electric charge E that's equal to, just comparing it with this formula here, G2 times sine theta omega. And in some sense, this is the definition of electric charge. This is how electric charge arises from the SU2 times U1 electroweak theory. And similarly, the W minus boson has opposite electric charge. So, in particular, the Glashow-Weinberg-Salam theory has massive gauge bosons where the W plus minus particles are vector fields with charge plus or minus 1. In our interaction term here, this was just a standard derivative, not a covariant derivative. And so the Z bosons are vectors with charge 0. Here, of course, I mean standard electromagnetic charge. And the Higgs boson is a scalar with charge 0. Because it was a real scalar field, not a complex scalar field. And here, of course, I mean electromagnetic charge. I mean, it's worth, I've gone through this a little bit quickly, but it's worth sort of going through yourselves and understanding precisely how it is that these gauge fields acquire charge via the Higgs mechanism. Why these gauge fields look like they're becoming charged vectors after the Higgsing of the electroweak symmetry. I mean, roughly speaking, it's because the electromagnetism is a linear combination of hypercharge and T3, where T3 is the third Pauli matrix. It's a linear. It's the diagonal component here, and you can and remember that. So for fields in the adjoint representation, like the gauge field, the coupling term in electromagnetism is a commutator. If this is not clear, it will be by the time you do the problem set due Friday. And if you just work out what that commutator looks like, the commutator between two fields on the diagonal with one another is 0. That's why A mu and Z mu are uncharged under electromagnetism. But the commutator with the off-diagonal terms is non-zero. That's why the W bosons have charge. And because of charge conjugation symmetry, if you've got a particle with a plus charge, you also have to have a particle with minus charge. That's why the W bosons appear in a pair, one with charge +1 and one with charge -1. And then, of course, expanding out, the Higgs potential and the Yang-Mill equation in terms of A mu, W mu, and Z and H gives more interactions. So, you know, for example, you know, one of the interactions that you would get would be a coupling term. So just coming when you take, say, this term here and rewrite it in terms of the W's and the A's, you'll get various mixing terms. So for example, you get a term that looks like F mu nu 3. Sorry, you'll get a term that looks like, you know, F mu nu times W mu plus W mu minus. Where does that come from? That comes from the expansion of F mu nu 3 squared. Where, because F mu nu 3 contains a term that looks like D mu A nu 3 plus minus D nu A mu 3 plus G2 times some stuff involving the W's, right? So A mu 2, A nu 1 minus A nu 1, A mu 2, that's the commutator term in the covariant derivative, in the field strength. And so there's some W squared term there. Okay. So for example, this would lead to a term where, you know, a gauge boson can, or the photon can break apart into a W plus and a W minus. And then there'll be various other terms involving couplings of the W to the Z, as well as couplings of the W's with one another. So for example, let's just write it all out since I'm 90% of the way there. There's also a term involving a coupling of the Z to W, as well as a coupling of all of the various W's to one another. And then, so this is one term where, let's see, a W plus and a W minus W pluses and W minuses can scatter off of one another. So this is one term that describes, say, you could think of it as a W plus and a W minus with the same polarization, scattering into a W plus and a W minus with the same polarization. And then there's a second term involving a W mu plus, W mu plus, and a W mu minus, W mu minus. And then finally, there'll be also terms involving interactions of the Higgs field with the W's and the Z bosons. Okay. So that's it. These are the bosons of the Standard Model. Along with the gluons. That is to say, the SU3 gauge fields. The SU3 symmetry is unbroken, so there's nothing particularly fancy going on there. One aside that I'll make is that all of the formulas that I've written down here are in unitary gauge. And that for loop computations, it's often typical to use a different gauge, our psi gauge, which we already discussed in the context of Yang-Mills earlier in this class. I don't think that we're going to be doing any loop computations in the Standard Model in this class, especially given that this is the last week of class. So I'm not going to really bother working out this action in R psi gauge for you. But you should be aware that everything that I've written down here is sufficient for doing tree-level calculations. In fact, surely on the problem set that I'm going to hand out this week, I'll have you do some sort of tree-level calculation. I haven't decided which one in the Standard Model. But you're going to have to work a little bit harder if you want to do loop calculations. You would have to introduce ghosts, as usual in Yang-Mills theory, and you would have to be a little careful about how these ghosts are treated once your gauge symmetry is Higgsed. But this is all stuff that you essentially could look up, given what you know already. So this is the gauge sector of the Standard Model. What I'd like to do now is start talking about the matter fields in the Standard Model. But before I do so, let me pause and see if there are any questions. Any questions? Is this all more or less clear? I mean, all of this was just essentially an exercise in writing out gauge fields in the Higgs mechanism. So you're going to do a slightly different exercise on your problem set due this week when you work out the mass spectrum of some gauge fields for an SU5 gauge theory. That's Higgsed down to a very interesting subgroup of SU5. Any questions? Yes. So we'll get to quarks. We'll get to quarks. So quarks also. Yes. So far I've been talking about the force carriers of the Standard Model, otherwise known as bosons. Now we're going to talk about the matter fields. So there are two different kinds of matter fields in the Standard Model. And I'll start by talking about the leptons. Okay. So leptons are spin 1/2 fields that are color singlets. That is to say, they don't interact with the strong nuclear force. Quarks, on the other hand, do carry color charge. And there are 6 of them in the Standard Model. The electron, muon, and tau particle, along with their associated neutrinos. And these 6 particles are organized into 3 generations. That is to say, we have 3 doublets of leptons. Now, they're called generations, in fact, because the masses of a given so it turns out the quark fields are also organized into 3 generations, and the masses of the generations sort of arise in a hierarchy. So the lightest generation of leptons are the ones that you're most familiar with, the electron and the electron neutrino. But there are also the 2 heavier generations, the tau and the tau on neutrino, the mu and the muon neutrino, and the tau and its neutrino. One thing that I should make clear is that we describe these in terms of Weyl fermions rather than Dirac fermions. And this reflects the fact that the standard model is not parity, is chiral. It is not parity symmetric. Dirac fermions are parity symmetric. And in order to build a chiral model that violates parity symmetry, you need to use Weyl fermions. So let me just remind you about Weyl fermions. Okay. So a Weyl fermion chi is a two-component spinner which can be regarded as the left-handed part of a four-component Dirac spinner. In particular, if you start with a four-component Dirac spinner psi, then its left-handed part is PL times psi, where PL is the projection operator that projects onto particles of left-handed particles, those with gamma 5 equal to -1. And in the Weyl basis, this is just the top component of psi. We write psi as a two-component Weyl spinner on top of the two-component Weyl spinner. Now, in the Weyl basis, the gamma matrices are just given by, well, in 2x2 block form, a bunch of Pauli matrices. Here, remember that sigma mu is 1 sigma, sigma bar mu is 1 minus sigma. And so the action for a Weyl fermion, so for a massless Weyl fermion, is just I chi dagger sigma bar mu d mu times chi, where chi is our two-component Weyl spinner. And you could actually also equally well write that in terms of Dirac spinners. So as just the usual Dirac action, except where we insert a projection operator onto the left-handed part of our Dirac fermion. Given a Weyl spinner, we can also write down a scalar. So if you have, say, two Weyl spinners, let me not call that phi, I gave that name to the Higgs. If we have two Weyl spinners, then there's one scalar bilinear you can write, which is chi A psi B epsilon AB. So if you wanted to write down mass terms for a Weyl spinner, this is how you would do it. Okay. So that's something that at least you're hopefully a little bit familiar with. So let me now work out the matter content of the standard model for the leptons. So what I'd like to do first is just consider one generation. So that my coupling constants are a little bit simpler and I don't need indices everywhere. So what do we have? We have a lepton L, which transforms into two-dimensional representation of SU2 and has hypercharge -1/2. And then we have another particle, usually called E bar, which transforms in the 1,1 representation. So it does not transform under SU2 and has hypercharge 1. Now, we usually give names to the fields in this two-component doublet of SU2. The upper one I'll call nu, and the lower one I'll call E. So remember that because of the Higgs mechanism, we've broken this SU2 symmetry. So the Higgs particle, the complex scalar, was taken to have a vacuum expectation value that was pointing in the top, that was in the top component. Okay. That means that when you expand around the vacuum with a non-zero Higgs field, the two components of L will be treated differently. That explains why the neutrino and the electron, although they appear in the doublet under a gauge symmetry, actually have different properties. I mean, that's sort of an important point. You might think that the two components of some doublet under gauge symmetry would have the same properties, okay, because they're related by some symmetry. But if that symmetry is broken, as it is in the case of the Higgsing of the SU2 electroweak symmetry, those particles have different properties. That's why neutrinos and electrons have different charges and masses. One other point that I should make is that here, E bar, I'm using a kind of slick notation, a kind of horrible notation actually, but a notation that everybody uses. So the bar here is not, I'm not taking E and barring it, where bar is some operation. Bar is just part of the name of this field. Okay. So we have one field named E and another field named E bar. Okay. I could name it something different. I could name it Alex. One field named E, another field named Alex. Okay. I'm not going to do that though. I'm going to name it E bar instead. The point being though that bar is part of the name of this field. Although, of course, as we'll see if we get there, there are ways of rewriting the theory so that it looks like E and E bar form parts of a Dirac field, so that you could think of bar as some physical operation. But really, I want you to think of bar as just part of the name of the field. Okay, so what is the action? Well, the kinetic term involves a gauge covariant derivative. So what is that? This is partial derivative of that lepton field L minus I G2 A mu A TA. Okay, I guess I'll just leave off my indices. So these TAs, of course, are again 1/2 sigma A, those Pauli matrices, minus I G1 times B mu times the hypercharge of the lepton field, minus 1/2 times L, where L is some doublet. And similarly, E mu, so E bar has a covariant derivative, which is just given by minus I G 1 times B mu times the hypercharge assignment of E, which is 1. And the kinetic term is just the kinetic term for a pair of Weyl fermions generalized in the usual way to take into account the fact that these are fields that transform in some representations of the gauge groups. So, okay. There's a couple things to notice about this. The first very important thing to notice about this is that there are no mass terms. There are no possible mass terms that are compatible with both Lorentz and gauge symmetry. So how are these fields going to get mass? You know that the electron has mass. And the point is that, remember, we were instructed by Wilson to include all of the terms in the effective action that are consistent with gauge and Lorentz invariants that are renormalizable. And there's one renormalizable type of term you can add, which is a Yukawa interaction. I mean, this lecture is really great. We're really using every single goddamn thing you've learned this year. So there's a Yukawa interaction. Remember that scalars can interact with fermions. So there's some interaction of the form phi times L times E bar plus Hermitian conjugate. Y here is a coupling, the Yukawa coupling. And we need to make sure all of our indices are contracted together appropriately. So phi and L both carry 2 index under the SU2 gauge symmetry. And so if you want to form a singlet from that, something that's gauge invariant, you can just contract it with an epsilon ij. And L and E bar also include they also have a doublet index, which is the spin 1/2 Weil index. And those are contracted also using the epsilon symbol, which I guess I'm not going to write out explicitly, but I guess I could. Okay. It would be Lj A, Ea, Eb, epsilon AB. Okay. So the symmetry structure of the standard model allows us only to write down this particular type of interaction. Okay. So this is a interaction between our Higgs particle, our Higgs field, and these leptons. We expect it to be there because it's a renormalizable term. And if we go ahead and expand around the state where phi has a non-trivial expectation value, this leads to a mass term. And what is the mass term? Well, we get a minus y over root 2 out front. And so phi, we just replace it by its vacuum expectation value. And so it was proportional to v comma 0. And what did I call L? L had a nu in its top component and E in its lower component. So we contract with the two-dimensional epsilon symbol. And you get V times the second component of the lepton field times E bar plus Hermitian conjugate, otherwise known as E bar plus Hermitian conjugate. So this is how the leptons get mass. So the leptons get their masses from the Higgs field. This is the origin of the slogan that the Higgs field is what gives masses, explains the masses of all of the particles in our universe. And the reason why one of the leptons gets a mass and the other one doesn't is that the only gauge invariant combination you can write down that pairs the Higgs doublet with the lepton doublet is via this epsilon symbol, epsilon ij, which gives the lower component a mass, but does not give the upper component a mass. So if we wanted to, we could assemble E and E bar into, so you have two component file fields. So you have four component, you have 4 degrees of freedom. Well, okay. You have 4 functions. And so we could define a field that I'll call capital E, which is a Dirac spinner, where I assemble an E and E bar into one gigantic 4-component object. So this would be the electron Dirac spinner. And then this mass term is just the usual mass term that you expect for a Dirac field. Good. Any questions on this? Okay. So the leptons all carry charge under SU2 and U1, which means that they should carry charge under U1 electromagnetism. And so we could go ahead and work that all out. Okay. So in particular, remember that in the covariant derivative, the charge terms, the couplings to charge, well, they'll look like this. So in the present case, so if we just go ahead and rewrite A3 and B in terms of A, mu, and Z, what will you get? Well, we can just go ahead and remind ourselves of what that looked like. So you can just remind yourself of this here. So A3 is a linear combination of A and Z, and B is a linear combination of A and Z. So if you just work that out, you get E times T3 plus Y times A mu plus another contribution proportional to Z. So what does that mean? That means that the electromagnetic charge, which we could call Q, what is that? That's T3 plus Y. So remember that the electromagnetic U1 gauge field is some combination of the A3 SU2 gauge field and the U1 hypercharge gauge field. And so that means that the charge of some object is some combination of the behavior of a particle under SU2 and its charge under the hypercharge gauge field. So in particular, if you think about, so for example, the neutrino, so L, the lepton doublet, was a neutrino on top and an electron on the bottom. So that means that T3 of the neutrino is 1/2 neutrino. So the neutrino has a T3 charge equal to plus 1/2, whereas the electron, if you acted on it with the third Pauli matrix divided by 2, would be minus 1/2. And so the charge of the neutrino is T3 plus Y on the neutrino. And remember, the lepton doublet had hypercharge minus 1/2. So neutrinos don't have charge. Whereas on the electron field, you have T3 plus Y. Of the electron field, that's equal to minus 1 times E. T3 on E is minus E because it was the lower component of this SU2 doublet. So if you act on it with minus 1/2 times the third Pauli matrix, you get minus 1/2, and the lepton field had charge minus 1/2. Whereas Q of E bar, well, T3 is just equal to 0 in that case because, well, E bar was a singlet under the SU2 electroweak symmetry, but it had hypercharge 1, so it has charge plus 1. So what we see is that, if we go back, just to sort of summarize, to all of these somewhat random-looking charge assignments of the particles in the Standard Model, a lot of that is just summarizing things that we already know. We're summarizing the fact that, well, the neutrino doesn't have charge, and the electron has charge plus 1, the positron has charge, electron has charge minus 1, positron has charge plus 1, and so on and so forth. Any questions on this so far? I mean, I'm really not doing anything fancy. All I'm doing is working out in somewhat gory detail a specific case of the Higgs mechanism. Yes.
A couple lines up.
Mm-hmm.
Questions up
Yes.
Is that sine theta W times cosine?
Yes, that's sine times cosine. Sorry, I just didn't have room to write it. I can probably write it. Yeah. I mean, if you go through and work this all out, I'm skipping bunches of algebra steps because that's life. But, yeah, question.
So we wrote about that the electric charge is T2 times sine theta W.
Yes.
Like that. Okay. So the running of the capacity, as we know it completely agrees with the running of G2 and theta.
Yeah, that's right. I mean, of course, if you wanted to compute, in the Standard Model, the electromagnetic gauge field is just a name that we give for this fancy combination of SU2 and U1. And if you study the theory, say, at energy scales, at sufficiently high energy scales, there is no electromagnetism. There's just SU2 and U times U1. Okay? And so it's really the gauge couplings G2 and G1, the gauge couplings of the two gauge theories that run at high energies. And at low energy, you can't really say which one of those is the electromagnetic field at high energies, if you know what I mean. To some extent, at energies far above, 100 GeV or whatever, there's no distinction between the electromagnetism and the other W and Z, the other forces carried by the W and Z bosons. Yeah. So when we say running of right. When we were studying QED, we studied a very simple example where if you imagine that you just have electrons and photons all the way up, for up to arbitrary high energies, then you would have this running of the electric charge and the Landau pole and all that stuff. But really, of course, there's new physics that comes into play. In fact, what you called electric charge was just some linear combination of some other gauge fields. It may well be, in fact, it seems very plausible that what we call, what we think today are the fundamental forces in the Standard Model are not fundamental, the same way that electromagnetism was not a fundamental force. It just turned out to be one manifestation of some other force that only became apparent at high energies. So it certainly could be the case that, the various gauge fields of the Standard Model themselves, those coupling constants really don't mean anything when you get up to high energy because these are all, coupling constants of some more fundamental gauge group. That's grand unification. As you can probably tell, based on comments I've made, I think it's a pretty reasonable model for what happens. It seems very plausible. But we just don't know. Okay, and now based on this, there are going to be various other couplings between, say, the electrons and the neutrinos and the W and Z bosons, which you could work out. So, for example, these leptons couple to the W's to the gauge bosons in the usual way. So that means that in addition to couplings between the electrons and the neutrinos and electromagnetism, as we described above, there are going to be couplings to W's and Z's, which are straightforward to write down. I'm out of time, so I won't do them now. But depending on how things go, maybe I'll write them down for you next class. So, it's sort of amazing. We managed to put together all sorts of ingredients that we've developed over the year to write down at least the electroweak sector of the Standard Model. And as we'll see next time, in some sense, the quark sector is quite simple compared to the electroweak sector because there's nothing too fancy involving symmetry breaking or anything like that. So this is where I should probably stop for the day, but I'll see you on Thursday when we finish writing down the Standard Model. Any questions before I stop? Yes?
What is a generation? Is there a natural reason for organizing the fermions in that way, or is it just an observation about the distribution of masses?
It started as an observation about the distribution of masses. In grand unified theories, it's very natural. So, for example, my favorite grand gut model is based on SO10. And in that model, all of the fields in one generation are organized into one single giant matter multiplet. And so it's natural to imagine that you just have 3 copies of this multiplet. Okay. So, it's kind of a remarkable thing. Why, I told you that the leptons are organized into generations, electron, muon, tau. In terms of the quarks are organized in generation. There's up, down, strange charmed, top, bottom. So why do the quark sector and the lepton sector both have these 3 generations? Why is there this symmetry? Why is there this similarity between the way that the quark sector and the lepton sector are written down? Well, the natural reason to expect that there's a similarity between those 2 structures is that they're actually related by symmetry. Right? And that's one of the things that grand unification does for you. There are other sorts of symmetries that people postulate that might be related to this. But it's still an open question. Yeah. So the question of where, it's like, the question of where do the coupling constants of the Standard Model come from? I don't know. It's a good question. Good. Any other questions? Great. Okay, see you on Thursday.